Welcome to the lesson on 2.3, the limit laws. At the top, basic limit laws. There's two for any real number a and constant c. If we take the limit as x goes to a of x, it's just a, and the limit as x goes to a of c is just c. Basically saying that a constant function will stay the same, and the limit will change and vary with x. It'll go to a. Let's take a look at the two examples. The first one, limit as x approaches 7.2 of x, just 7.2. The second one to the right, the limit as x goes to 500 of 7. The 500 has no effect on this since it's just a constant function 7. It will always remain 7. Okay, let's look at some other limit laws, going over these kind of quickly, and we'll take a look at some examples later that will walk us through this. So the setup is if there's two functions, f and g, that are defined for everything, with the exception of x maybe being a, we're going to look at two facts. One is the limit as x goes to a of f of x is L, and the limit as x goes to a of g of x is M. In other words, they both have a limit. And anytime we see c in the following statements, we're going to consider that to be a constant. So the first one is called scalar multiple, basically saying if you take the limit of a function with a scalar multiple, that scalar multiple can be pulled out front and multiplied by the value of the limit later. Same is true for sum and difference here. We're saying that if we take the limit of two functions being added together, you can actually take the limits independently and add or subtract them later. It's also true for the product and the quotient, that you can do the limits first and then do the multiplication and division later. You need to be careful in the quotient rule, of course. You can't have a limit of 0. That's the one exception. You can't divide by 0. There are similar rules for power and root. You can take the limit of a function and then apply the power later, and you can also take the limit of a function and apply the root later, and we'll look at some examples of those as we go on. Let's take a look at these three examples for warming up. The first one is the limit as x goes to negative 3 of the expression 4x plus 2, or the function 4x plus 2. We can apply those limit laws, but we're going to get a lot faster at it in a little bit. The first one is we can apply the limit law of multiple, and that is, and we can also split it up. I'm going to do two of the properties at once. On the first term, 4x, I'm going to think, okay, 4 is just a scalar multiple. That's the limit as x goes to negative 3 of x. But the addition sign here, I'm going to say, let's take another limit, a limit as x goes to negative 3 of just the constant 2. So I'm treating that as two separate limits. So what do we get? Well, let's see. The first one, remember the property from above, x goes to negative 3. This just becomes a negative 3 here. And the second one is a constant. It stays 2. If we evaluate 4 times negative 3 plus 2, we should get negative 10. Now, if you think back to the original one, you could have just plugged in negative 3. It's kind of the same thing. We're going to look at some other examples where that is not quite so straightforward as we go through this. The second one, now that we have this in our minds, we can think, oh, this looks like a quotient. Maybe I'll just think about plugging in 2 and see if it works out. If we plug 2 into the numerator, we have 2 times 2 squared minus 3 times 2 plus 1, all over 2 cubed plus 4. We don't have a problem in the denominator with a 0. We can just evaluate that. It looks like it will be 3 over 12 if we evaluate that, simplifying to just a value of 1/4. On the last one as well, it doesn't look like we're going to have any issues. We can think about this as being multiplied, two separate things. Let's just plug in the 6. So we have 2 times 6, subtracting 1. I'm going to multiply that value, whatever we get there, times the square root of 6 plus 4. And so on the first piece, we'll get 11 times the square root of 10. And that's as simple as we can make it. We'll just write it as 11 square root of 10. Moving on to the next page, we're going to look at a lot of other limits where we get what's called an indeterminate form. And the one to consider the most is 0 divided by 0. Remember that when you divide by 0, you get an error, but 0 divided by 0 can actually have an infinite number of answers. And that's because 0 times anything is 0. So here are four different methods that we'll be using and highlighting. Try factoring and simplifying. That might work out. Try multiplying by a conjugate. If you remember what a conjugate is, if you have something like a plus the square root of b, the conjugate of that would be multiplying by a minus the square root of b. That's just an example. Number 3, simplify any complex fractions. And number 4 is, well, it's not a real official method, right? I just wrote mix it up. What does that mean? Try something. Do something. Don't break any algebraic rules. Just see what you can do to simplify, maybe rewrite in a different form, and apply limit laws when you can. Okay, so taking a look at the very first one, it looks like we have a polynomial over a polynomial. Let's try the factoring technique. That's the first technique. In the numerator, we'll factor out an x, and in the denominator, we will notice that it's a trinomial. It's likely a binomial times a binomial, so 2x times x gives us the 2x squared, and then the last term, negative 3, we're going to have a 3 here and a 1 here. It looks like I need a negative and a positive. Do a quick check to make sure that that works out. It looks good. Notice that we have these two factors that can simplify, and we're left with the limit as x goes to 3 of x over 2x plus 1. So it's going to behave like this. Now when we plug in 3, we shouldn't have an issue. And I did not mention this earlier, but if you would have plugged in 3 here, in the original one, you would have got a 0, and if you would plug in 3 on the top, you would have got a 0. That would have been a 0 divided by a 0, which is this indeterminate form. But anyway, I neglected to tell you that, but that's why we're simplifying. Now let's plug in that 3, and so we have a numerator of 3. And on the bottom, we have 2x plus 1. Plugging in 3, we should get 7. So 3/7 will be our answer there. You try the one on the right. Now that you tried the one on the right, maybe you noticed that in the green box above, I had some reminders about factoring. We can apply this very last one, the a cubed plus b cubed. Notice that 27 is actually 3 cubed. So the numerator will factor as a plus b. That'll be x plus 3. And the denominator will factor like this, a squared will be x squared minus 3 times x plus 9. That's the 3 squared over x plus 3. And we can simplify this. Then try plugging in our value of negative 3. We're taking the limit as x goes to negative 3, so we get negative 3 squared minus 3 times negative 3 plus 9, which will be equal to 9 plus 9 plus 9, or 27. Okay, let's take a look at this next example, which will combine a few of the techniques. So this one is the conjugate technique. So we're going to multiply. I'm going to change this equal sign to a multiply. We're going to multiply the numerator by the conjugate, which will be the square root of x plus 2 plus 1. We're going to change that minus to a plus. Let's multiply the numerator by, the denominator by the same thing, not to change the value of the limit that way. So square root x plus 2 plus 1. So the cool part about a conjugate is watching what happens as you multiply the terms. So the first part, square root x plus 2 times square root x plus 2 is basically square root x plus 2 squared. That will just give you the inside x plus 2. And remember, with a conjugate, the middle terms drop. We get 1 square root x plus 2 minus 1 square root x plus 2. Those cancel out. And lastly, negative 1 times 1 minus 1. In the denominator, I'm just going to leave the first factor, x plus 1, times this conjugate factor, square root x plus 2 plus 1. So let's just simplify the top slightly. We have x, and then 2 minus 1 is just 1. Now notice that that factor happens to match a factor in the denominator. And again, that looks just like the technique that we did before. So now those will simplify out, leaving us with 1 over square root x plus 2 plus 1. Now, I have a little bit of an issue with notation as I went through. I was being a little lazy, so let me just go back and fill in the details. I didn't write my limit, but again, it's a limit as x goes to negative 1 there. This is the limit as x goes to negative 1 there. So we're still doing that limit as x goes to negative 1, but now I don't have the 0 over 0 issue, so I can go ahead and plug in my negative 1. And so we will get 1 over square root negative 1 plus 2 plus 1. And so square root will be 1 plus 1, 2, 1/2. All right, you go ahead and try the one on the right. Okay, now that you tried that, you should have gotten multiplying by the conjugate here of square root x minus 1 plus 2 over square root x minus 1 plus 2. Keep that identical, and then equals the limit as x goes to 5. By the way, you should have ensured that when you plugged in 5, you get indeterminate, which you do. On the top, you're going to get square root x minus 1 times square root x minus 1. That's just x minus 1. Middle terms drop, minus 4 over the denominator that just is going to be x minus 5 times that. I'm just going to recognize that it's there. Going to the next line. If you simplify the numerator, negative 1 minus 4 is going to be x minus 5. That will just beautifully simplify with the x minus 5 in the denominator, but you'll still have that square root x minus 1 plus 2 piece, and now you can just plug in the 5. When the numerator is just a 1, if you plug in a 5 for x, you'll get square root 4, which is 2 plus 2, or 4. So you should have gotten 1/4. All right, let's take a look at one with a complex fraction. So our strategy is basically going to be to eliminate the complex fraction, just to work with the algebra a little bit. So in the numerator, we have 1 over x plus 1 minus 2. Minus 1/2. So we're going to use a common denominator approach. Our common denominator will just be a combination of x plus 1 and then times 2. So we're going to multiply the first fraction on the top times 2 over 2, and then the second fraction on the top will need to be multiplied by x plus 1 over x plus 1. All right, so we got quite a bit of algebraic technique. The denominator will just leave as the x minus 1. So that's going to be equal to the limit as x goes to 1. On the top, we're going to get, let's just take a look at the pieces. In the first fraction here on the left, we're going to get 2 times 1 is 2 over the common denominator of 2x plus 1. I'm going to go ahead and combine it with the fraction on the left because it's, well, let me do it in 2 steps. I don't want to do it in 1 step yet. We'll maybe jump to that later. So the one on the right, because we're subtracting, is we're going to distribute the 1, so it's just going to be x plus 1 over the common denominator of 2 times x plus 1. And maybe you can see why I didn't skip a step here. We do have this subtraction sign, so it's going to basically distribute to both of those terms. So moving on, let's go ahead and do that subtraction now that we have a common denominator. So we have 2 take away 1 is just 1 minus x, because that's also being subtracted, over the 2 times x plus 1. And all of that is being divided by x minus 1. So I'm going to write it like this a little differently so you can see my strategy here. So again, we're still doing the limit as x goes to 1. So then the last thing you can think about simplifying it is that this factor of 1 minus x almost looks like the factor of x minus 1. They're just in reverse. So you might remember the little factoring technique or trick, which is to factor out a negative. So I'm going to factor out a negative, and then I'll get negative x minus 1 over 2 times x plus 1. And if I divide by x minus 1, that's the same as multiplying by the reciprocal. And now I'll get the cancellation, or should I say simplification, that I really wanted, and I'll be left with just a negative 1 over 2 times x plus 1. Let's go ahead and plug in our value of x as x goes to 1. And the numerator, I get a negative 1. The denominator, let's kind of think this through. Plugging in a 1 for x. 1 plus 1 is 2, times 2 is 4. So we're going to have a limit of 1/4. You would try the same thing with the one on the right. Okay, without working out all the details, you should have gotten an answer of negative 1. You can ask me more about that in class if you did not get that solution. Let's take a look at this last one, which I'm calling mix it up, which means there might be a combination of things going on. So on this one, I noticed that there's 2 fractions, so I'm thinking we probably need a common denominator. They do have a common factor of x, so I just need to take this first fraction here, 1 over x, and multiply it by x minus 5 over x minus 5, and I should get a common denominator. Now, before I continue, let's just think about the limit as x goes to 0. If you were to plug in 0, you can see you get 1 over 0. That's an undefined expression. And on the right, you'd have 5 over 0. That's also undefined. We don't exactly have the 0 over 0, and that's because we have 2 terms rather than 1. If we were to put these fractions together, we might notice that we would get a 0 over 0. So let's continue. So I'm going to multiply the first fraction, 1 over x, times the missing factor, x minus 5 over x minus 5. And then I'm going to keep the second fraction, that's this piece over here, I'm going to keep that all the same. That's 5 over x times x minus 5. Now I'll have a common denominator. So let's kind of work through that. Oh, I can see this pin is a little too large. Let me size that one down just a tad. All right. So the limit as x goes to 0 in the first fraction. If we just multiply out, we have 1 times x minus 5 is just x minus 5. But we're going to be adding that to plus 5. So notice that the minus 5 and the plus 5 will cancel out. We'll just be left with x over the common denominator x times x minus 5. Now you can notice, yeah, it is that indeterminate form. When you plug in 0, you in fact do get 0 over 0. But in this format, something really beautiful happens, is the x's will simplify out. We'll be left with the limit as x goes to 0 of 1 over x minus 5, and now we can just simply plug in our 0, giving us an answer of negative 1/5. You try that one on the right by mixing it up. I hope you made a lot of progress on that one. Maybe it was a little bit tricky. That was on purpose. You might notice that the fraction on the right, if you factor the denominator, it actually factors to x minus 3 times x plus 1. So they do have a factor in common, that being x minus 3. And so you can just multiply this first fraction. You can multiply that by x plus 1 over x plus 1. If you didn't try that, go ahead and pause the video again and try that piece. Anyway, if you work out a lot of the details, right, sometime later, you should have gotten an answer of 1/4. And you can ask me about that later or in office hours if you did not get that. But anyway, keep working with it if you have not yet gotten it. Let's go ahead and move on and take a look at something else. What if we have a piecewise function? You might remember these from your algebra course where the function comes in part. This is a two-part piecewise function. We're going to consider it the function to be 4x minus 3 when x is less than 2, but it's going to be x minus 3 squared, quantity squared, when x is greater than or equal to 2. Evaluate the following limits. And so we're going to have one-sided limit here for the first one, and that is the limit as x goes to 2 from the left. Remember when we write 2, but we have a little minus sign right there, we're seeing coming in from the left-hand side. Maybe I can give you a little bit of a visual to think about this, and let's think about this function as a graph before we go back and think about these, evaluate these. So the first function, 4x minus 3, that's just a line. Slope 4, y-intercept negative 3, but that's when x is less than 2. So if here's our breaking point, where x is 2. But let's think about graphing that line. The y-intercept is negative 3, so this is not going to be a very great graph because I'm not using graph paper. The slope is 4, 1, 2, 3, 4 over 1. So it's going to be, pretty steep like this, all right? But it's going to stop here. It's going to be an open circle at x is 2, and it's going to go down forever. So it's only going to be to the left. When we get to the other part, which is when x is greater than or equal to 2, we're going to not have a linear function anymore, but rather a quadratic function that's shifted 3 spaces to the right. And if you remember that, great. But anyway, that would be centered about right here when you plug in 3. And so it will do something like this. It'll go about like that. That's not a perfect graph. It gives you the idea. So you can see that there's an issue at 2 where it jumps from one to the other. Now, you don't have to know that to be able to do this, but it's kind of nice to see the visual to see what's going on. So as we're coming in from the left at 2, you can see we're coming in from the left. I'm coming in, getting closer and closer and closer. What value am I approaching? I'm approaching the value on the left function. So I'm really going to plug it into this piece right here. All right, so let's do that. So we're just going to consider, all right, let's plug in 2 to that left function. Now notice, if we plug in 2, that's something different, all right? But we're taking the limit as x goes to 2 from the left. That will be 8 minus 3, or 5, all right? Whereas, if we come in from the right, we're coming in from the right, getting closer and closer and closer and closer. We're getting close to this point here at the bottom. So we're having to plug it into this function. That's the secondary function. So we're going to plug it into x minus 3 squared. And we'll get 2, subtract 3 squared, or negative 1 squared, or 1. So if you come from the left, it approaches a value of, I'll show you on the graph, if you look over that graph, 5 right here. But if you come in from the right, it approaches a value of 1 right there. All right, so what is the limit as x goes to 2 of f of x? Well, since the left and the right-hand limits are not the same, this does not exist. All right, there is not one singular value that it converges to from the left and the right. So we don't have that limit. Let's move on. All right, so I have a little statement here. The techniques we have developed thus far work very well for algebraic functions, but we're still unable to evaluate limits of trig functions. There's something called the squeeze theorem that's useful for establishing basic trigonometric limits, and there's a really nice proof in the text, and you can check that out. But here's that squeeze theorem. So let f, g, and h be defined for all x not equal to a over an open interval, and let L be just an element of the real numbers. That's what this means right here, that notation, let L be any real number. So we have this theorem that if f is less than or equal to g, which is less than or equal to h on the interval, then the limit of f of x as x goes to a as L is equal to the limit as x goes to a of f of x, h of x. Like if that's true, this is an if, right? Then it must be also true that g of x is equal to L. In other words, if g is between f and h are both L, then you would just then verify that g would also be L. So let's apply that to the picture below. So what we have here is the little right triangle. We have on the interval from 0 to, we're thinking about the interval from 0 to pi over 2. That's that first quadrant interval. You notice that sine of theta is less than tan. And so, well, what do we mean by that? So you can take a look at the picture to kind of give you a sense of the height, the size of sine theta, and the height of tan theta. Remember that our adjacent side, or you could also call it the x value, is just 1 here on that unit circle. So we can certainly know that that's the case. And we also know that the value of theta is this length here. And so since that's that curve, that's why it's going to be a little bit larger than your sine theta value, because that's just a straight line. So it's just using reasoning from the picture. So if you divide everything by sine theta, that is to take this expression here and divide it by sine theta, the first term will be 1. The second term will be theta over sine theta. And the last one, if you divide tan theta by sine theta, maybe we better do a little work on that if you don't remember that from your trig class. But you might remember that tan can be rewritten as tangent is actually equal to sine theta over cosine theta. But we're going to be dividing that all by sine theta, which is the same as multiplying by the reciprocal sine theta. And so we're going to get 1 over cosine theta. All right. So if you compare the reciprocals, let's see what happens. So you need to know a little something about comparing reciprocals, but maybe this will make sense. This is just the proof of it, is that the reciprocal of 1 is just 1. The reciprocal of theta over sine theta is, well, just kind of using the notation of reciprocal there. And I don't really like that pen color. And the last one, the reciprocal of 1 over cosine theta, will just be cosine theta over 1. But when you compare reciprocals, so each one of those is taking the reciprocal, what it does is it changes the direction of the inequality. All right, now we're going to apply the squeeze theorem. So what I want to think about is I want to think about the limit. What's the limit as theta goes to 0 of this middle piece is really what I'm going to think about. But to do that, I'm going to consider all three of them. So that as theta goes to 0 of 1, that should be greater than the limit as theta goes to 0 of sine theta over theta, which should be greater than the limit as theta goes to 0 of cosine theta. Now, the one on the left, that's just a constant function. That's just going to be 1. The one in the middle, well, we don't know that one. What is the limit as theta goes to 0 of sine theta over theta? Pretty unsure, and here's why. If sine of 0 is, yes, you remembered, 0. And then 0 over 0 is our indeterminate form. So we don't know that. But we can't just cancel out thetas. That doesn't make any sense because this is a function on the top. However, something cool happens on this last one. What is the limit as theta goes to 0 of cosine theta? That's just cosine of 0. Cosine of 0 is 1. Oh, you see it? Yeah. This is 1, and this is 1, and this is between those. That must mean that this expression is also equal to 1. That's the proof using the squeeze theorem. So we have two important trig limits. The one on the left is the one that I just proved. The limit as x goes to 0, sine x over x is 1. The one on the right I will not prove, but it's the limit as x goes to 0, 1 minus cosine x over x is also equal to 0. You can use a similar type proof to get at that. So let's get on and take a look at our last page, which have some limits with trig functions. Let's take a look at our first one. The limit as x goes to 0 of 1 minus cosine x over sine x. If we just were to plug in the 0, we would get 0 over 0, giving us that indeterminate form, so we have to do some more work. But you might notice that these look very familiar to the two things that were proved from above, right? That is the sine x over x and the 1 minus cosine x over x, although it is missing the x. So we can do a little algebraic, I guess, trickery. We're going to multiply by 1 over x over 1 over x. And what we'll get is we'll get the limit as x goes to 0 of 1 minus cosine x over x all over sine x over x. Cool, we can use the quotient rule now. We can independently take these two limits. The bottom one is the proof that I did above. That one will just be 1. And the top one is the one that I did not prove, but it's that other limit that will be 0, and 0 divided by 1 is 0. Thus, our limit is 0. Let's take a look at the one on the right. The limit as x goes to 0 of tan x over x. Now, we don't have that, so we can use some trig identities. You might recall that tan x is equal, and I did this earlier, sine x over cosine x. So I'm going to rewrite this as the limit as x goes to 0 of sine x over x. But then the cosine x I can think of as coming down to the denominator. I can then use the limit law that allows me to think about this piece, sine x over x, times the other piece, the limit as, I'm writing limit twice, am I not? The limit as x goes to 0 of 1 over cosine x. I write the 1 because, there's something there. So this first piece on the left, that's the one that we proved. That's 1. And then the one on the right, I can just plug in the 0. And that's because cosine of 0 is 1. So 1 times 1 being 1. That's our value there. Okay, take a look at a couple more, and then we'll be finished. Okay, the next one, limit of tan x over sine x. You probably know what to do. Go ahead and try it. Okay, now that you tried it, at least I hope that you tried it, let's take a look at it. The limit as x goes to 0. The tan x on the top will be sine x over cosine x, but we're dividing by sine x, which is the same as multiplying by that reciprocal, so you should have gotten cancellation there. Then you can just think about plugging in the 0. Cosine of 0 is 1. Final answer, 1. All right, the one on the right, a little tricky, but once you see the technique, you can probably apply it to the very last one at the bottom left. Notice it's very close. We have sine 2x over x, but to apply the rule from above, these need to match. If this says 2x, this needs to say 2x. In other words, that has to be that same angle. So we can do a little manipulation here by multiplying by 2 over 2. Now, remember that on the top, when I write sine 2x, 2x is part of the sine function. All right, so that 2 that I'm multiplying there on the top doesn't get multiplied inside the angle. Rather, it's just a multiple to the sine function itself. So it's still sine 2x, but times 2 out front. And then on the bottom, I have 2 times x, or 2x. Now notice I do have the match that I want. This looks like my theorem above. In other words, the angle piece matches this expression on the bottom. 2x is 2x. So I can apply that limit law. And, well, I don't need to write limit again. I just have this 2 out front. Okay, so that's going to be a 2, constant, multiple. And the piece on the right we've already talked about is 1. So final answer, 2. You can try the one at the bottom left. Okay, now that you've tried it, let's take a look at this one. We can do a couple things. There's a couple things to consider here. It's kind of combining the tricks. If we multiply 1 over x times 1 over x, we will first get the limit as x goes to 0 of sine 3x over x all over sine 5x over x. Now I'm going to do another kind of multiplication, that piece that I could do in the second problem. I want these to match, so I'm going to multiply the top fraction by 3 over 3. I'll multiply the bottom fraction by 5 over 5. This is pretty cool for me because that makes this piece 1. That makes this piece 1. Remember, we can do these independently. And we're just really left with those multiples of 3/5. We're going to get 3 times 1 over 5 times 1. Final answer, 3/5. Okay, that sums up section 2.3.